Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will give a proof of a theorem called the law of large numbers. The basic idea is that with the aid of the inequality of Chevy-Chev, we will show that the expected value of a random variable for large n has high probability of being close to the sample mean x bar or y bar. Okay, so let's begin. Okay, so before we can show that theorem that I mentioned at the beginning, we have to we're going to need a couple of things first. One, the definition of convergence in probability, because it turns out that another way of thinking about our result, our theorem, the law of large numbers, is saying that the sample mean converges in probability to mu, the expected value of a random variable. Okay, so we need the concept of convergence in probability. Okay, so this is basically the definition of convergence in probability. So we have a sequence of random variables, x1, x2, x3, xn, and we keep going, right? So that sequence of random variables is said to converge in probability to a constant, to a number c, if for every positive epsilon we can show that the probability of the absolute value of xn minus c is less than or equal to epsilon, with probability 1 as n goes to infinity. Or if we don't want to show this, alternatively we could show this, that the probability that the difference in absolute value between our sequence xn and that constant that we have as our candidate for the limit, right, this difference in absolute value is bigger than epsilon, greater than epsilon, with a probability of 0 as n goes to infinity. Okay? Okay. So it turns out that for our proof we are going to be using this as our definition to show convergence in probability. Okay? Okay. Now the other result that I mentioned from the very beginning, right, was Chevy-Chev's inequality. Remember, we talked about it in sta258. Okay, so the idea is this: we have a random variable with a finite mean mu, variance sigma square, and then we have a positive quantity k. So in sta256 we showed this result, right? Remember, we used Markov's inequality to show this. Anyway, so what Chevy-Chev's inequality is telling us is that the probability that the absolute value of this difference, x minus mu, the random variable minus its mean, is greater than or equal to k, is less than or equal to sigma square, variance, divided by k squared. Okay? So very general. Okay. Now, before we actually give a proof of this result, I would like to show a particular case. And once we understand that particular case, you'll see that the proof is very simple. So here we go. So we have a sequence of independent Poisson random variables, okay? And the parameter for that Poisson is lambda. And you know, in this case we have a value for lambda. Lambda happens to be 3. What we would like to show is that if we compute x bar, right, and we have this subscript to underline the fact that x bar depends on the number of observations that you have here, right, the number of members that you have in that sequence, right? So we want to show that x bar converges in probability to 3, and we know that the expected value of a Poisson random variable is 3, right? So let's try and show this for a Poisson random variable. Okay, so first example, so we have xi has a Poisson distribution with parameter lambda equal to 3, right? So in our textbook, if you don't remember, we can check. Give me just a sec. Okay, I'm back. As I was saying, if you don't remember, right, what the probability mass function, the expected value, and the variance of a Poisson looks like, well, you could refer to page 837 from our textbook, right? And there you will find a table of the most common probability distributions, both discrete and continuous. So that's a probability mass function for Poisson. The mean, the expected value, happens to be lambda. Variance happens to be lambda as well. Okay? So now we can say, recall that the expected value of xi equals 3, right? And variance as well. Variance of xi is going to be 3 as well. Okay? Now, why I am mentioning this, right? Because what we want to show is that xn, meaning the sample mean, converges in probability to 3, right? So we want to show that x bar n, right? Oh, sorry. X bar n converges in probability, right? In probability to 3, right? Okay. Now remember that we have a definition of convergence in probability, right? It was the first slide that I showed you. And we said that we could use this or this, right? So we would like to show that the probability that x bar n minus 3, because that's the constant that we're interested in here, right? We want to show that the probability that x bar minus 3 in absolute value is greater than epsilon with probability 0 as n goes to infinity, right? Okay, so in other words, we want to show that the limit as n goes to infinity, right, of the probability of the following event, x bar, well, the absolute value of x bar n minus 3 greater than epsilon is 0, right? And we want to do this for any epsilon that is positive. Okay, so we would like to show this. This is what we would like to show. Now, we said that the basic idea, the main thing here, is using that inequality, Chebyshev's inequality, right? Okay. So that's the next slide. Okay. So first, let me remind you something. The guy that we're interested in here is x bar n, right? So note that the expected value of x bar n equals the expected value of what? What's the definition of x bar n? It's just 1 over n, and then we have the sum of x1 plus x2 plus x3 and so on, right? Up to xn, right? And that's why we are using that subscript to underline the importance of the number of elements in our sample. Okay? Okay, anyway, we have the expected value of that sum, which is multiplied by a constant, right? So we know that the expected value of a sum is the sum of expected values, so we could pull this guy out, that 1 over n, right? The expected value is linear, right? And then we have the expected value of a sum that's the same as the sum of expected values, right? Again, expected value is linear. Okay? Now, in this particular case, what we have is that the expected value of x1 is going to be 3. We have a Poisson with parameter lambda equal to 3. The expected value is 3 for all of those guys, right? So what we have here is 3 plus 3, so on, plus 3. How many times? N times. So what we have is 1 over n times 3 times n, right? Then in the end, clearly the expected value of x bar is just a beautiful 3. Okay? Now, so we found the expected value. Why? Well, because you know, the result that we want to use, Chebyshev's inequality, has to do with the mean of the random variable of interest and the variance of the random variable of interest. In our case, the random variable of interest is x bar. Okay? So we need the expected value of x bar. We need the variance of x bar as well. So let me copy paste this. So we have variance of x bar. It's the same as the variance of that quantity. So we could pull that guy out, right? That 1 over n, but we know that we have to pay a price. In this case, we have to square it. Okay? And then we have, we have to square it. Let me square it, right? There we are. And then we will have just the variance of a sum. Now, note that these guys, these xi's, are independent. Okay? So, since they are independent, and we have it there, let me see, let me go back to the statement of the problem. These guys are independent, and that is really important, because then we know that if we want the variance of a sum of independent random variables, then that is the same as the sum of variances, right? If they weren't independent, then we would need to take into account covariances. So things would be more complicated. But, well, thankfully, we have independence. So what we end up with here, right, is the sum of variances, which is nice. Now, given that each of these guys has a Poisson distribution with parameter lambda equal to 3, the variance of each of those guys is also 3, right? So let's write that down. We're going to have now 1 over n squared, right? Let me do that. I'll place the square here, right? 1 square is just 1, no problem. And then we have 3 plus 3 plus 3, how many times? N times, right? So we have 3 times n. And then in the end, what we have is that the variance of x bar is just 3 divided by n. Right? Okay. So now let me go back to Chevyshev's inequality. So our random variable of interest is x bar, right? X bar is a random variable with mean. In this case, mean is 3. Variance 3 divided by n. Then for any value k greater than 0, let's call it epsilon greater than 0. We will have that the probability of the absolute value of the difference between x bar and 3 being greater than or equal to epsilon is less than or equal to 3 divided by n divided, well, times epsilon squared. Okay? So let me just say that by Chevyshev's inequality, so first let epsilon be just a positive quantity, right? Now, by Chev's, right, inequality, we have that the probability that the absolute value of the difference between x bar and its expected value, mu, right, is greater than or equal to, instead of k, we have epsilon, right, epsilon, that is going to be less than or equal to sigma squared, the variance of the random variable, but the variance of a random variable is 3 divided by n, so less than or equal to 3 divided by n, which is the variance, and that variance is going to be divided by k squared, in this case epsilon squared, right? So what we have here is an epsilon squared. So we're just applying Chev's inequality to the random variable x bar. You guys agree? Okay, so now how about we take into account a couple of things, right? Probabilities are non-negative, meaning probabilities are greater or equal to 0, right? So recall, or just recall that probabilities are non-negative, right? What we want to say is that this guy here is greater or equal to 0, right? That is, that probability is greater or equal to 0, right? So it's bounded from below by 0, okay? And we have an upper bound for that guy, okay? So now what we're going to be doing next is just take the limit as n goes to infinity, right? Limit as n goes to infinity so this is going to be 0, right? So that's not a problem. Let me copy paste that one. Now note that as n goes to infinity, this is going to become small, 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 really small as we want. So the limit of this is 0. So this guy has no choice. The guy in the middle, the limit must be 0, right? So therefore, that limit is just 0, right? So what we have shown is that, you know, by definition, x bar converges, in this case, to 3 in probability. Make sense? Right? Okay, so now let me show you the statement of the theorem that we want to show. But again, before we do that, note that you have shown that x bar converges to 3 in probability. All that we had to do was use the definition of convergence in probability and well, Chevy-Chev's inequality for x bar. That was it, right? And well, we had to find the expected value of x bar and the variance of x bar, because that was the random variable of interest, right? But once we did that, it was game over, basically. Now let me show you the result, the theorem that we wanted to show in the first place, the weak law of large numbers. So we have a sequence, right, of random variables. They are independent, they have the same distribution, they are identically distributed, they have a mean, a finite mean mu, a finite variance sigma squared, and then for any epsilon greater than 0, we want to show that x bar, or x bar n, right, to underline the dependence, the role that the sample size plays in this. We want to show that the probability that the difference between x bar and the mean of those random variables, well, that the difference in absolute value between them is greater or equal to epsilon, goes to 0 as n goes to infinity, right? So what we want to show basically is that the sample mean converges in probability to mu, the mean, the expected value for these random variables. Make sense? Okay, now let me walk you through the proof. But in a way, you have already shown the result. Here goes. We want to show this. Okay, let's find the expected value of x bar and the variance of x bar, because we know we want to apply Chevy-Chev's theorem, right? Expected value of x bar, expected value of sum of xi's divided by n, doing exactly the same thing that we did here. You can show, instead of a 3, you're going to have mu, mu, mu. How many times? N times mu. So divide by n, you end up with mu. The expected value of x bar is mu. Variance of x bar, same thing that we did here. Variance of constant times a sum. You factor out the constant, you have to square it. Have the variance of a sum of independent random variables is the same as the sum of variances, and then the variance of each of these guys is sigma squared, sigma squared, sigma squared. How many sigma squareds? How many times you have sigma square? You have n times sigma square, right? And then it's just n times sigma squared divided by n squared, right? So you end up with sigma squared divided by n. Then just plug in random variable of interest, x bar, minus its mean, mu. Then for a positive epsilon, right, we have that the difference between x bar and mu in absolute value is going to be greater than epsilon, right? The probability of that is less than or equal to variance, which is sigma squared divided by n, divided by epsilon squared. As n goes to infinity, this goes to 0, we're done, right? Okay, so it was basically the same thing that we did here. This was just for a particular case. So we're done. Okay, so in summary, what you have to remember here is that x bar, the sample mean, converges to the mean, the expected value of these guys, of these random variables they come from, in probability, right? Or in other words, right, that as n increases, as the sample size increases, there's a high probability of the sample mean x bar being close to mu. Okay? Well, that's it. Excellent. We're done here. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.